I will explain you about the after you model and scale the response spectrum analysis results, you have to do the design of shear wall, column, and beam. I will explain column and beam. It is easy, but for the shear wall, it is a little bit complicated. Last time I already explained about the low combinations. You have to define the low combinations for the member design, and then you have to define the shear wall sections to do the design. First, in column section, you can define the reinforcement data in the definition, but in shear wall you cannot define. Here, for example, here in column you can define the rebar data, but in shear wall, when you define, you just define the thickness only. For example, here you define the thickness only, no reinforcement. And also, when you extract the forces of the shear wall, you will get the, if you do not assign the PR label, you will get the element forces. For example, here there are shells, you will get the shell stresses. After you analyze, if you want to see the shell stresses, you can see from this EQA's shell forces and shell stresses. This is F11 is the horizontal axial stress, F22 is the vertical axial stress, F12 is the shear stress. But okay, for F1, these forces are in kilonewton force per length. F11 will be kilonewton per meter. F22 also kilonewton per meter, and M11, M22 they are moment in meter, kilonewton meter per meter. So when you design, you are not going to design for each element that you measure. You are going to get the, you have to get the total shear force in the wall. So these element forces will not be used directly in the design. Stresses are in megapascal. It depends on your unit that you selected. So to get the total force in the shear wall, you have to define the PR label. For example, okay, for this shear wall, leg, if you want to get the bending moment and axial force and shear force for this leg, you have to define PR label, and the program will integrate the forces in these elements and give you the design force. So I will assign the PR label for this shear wall. I will select that shear wall, all story, and then assign shell area PR label. So after you assign the PR label, you can get the total force in that shear wall for each story. I will give the name SW1 and a new name. Okay, so you will see the PR label. This one already assigned. If you do not assign the shear pier level in other wall legs, you cannot get the force. After you assign the pier level, you can extract the pier force. Display, show table, wall output, wall forces, pier forces, and you can select any load combinations that you want to extract. For example, I will select 3A, 3B. So the program will give you the pier force for SW1 pier. For each load combination and for each story. Normally top and bottom forces are almost same, but for the axial load it is slightly different because of the weight of the particle members between the stories. So P is the axial force, V2 is the shear force that you have to design for that shear wall. It is in plane shear force of the shear wall. V3 is the out of plane shear force that we do not design. NT is the torsion, M2 is the bending moment, out of plane bending moment, and M3 is the in plane bending moment. This is the shear wall leg. So when you assign the pier level, pier axes are this one is 3, this one is 2, and one is perpendicular to that plane. So when we design the shear wall shear, we have to design for this V. We do not design for this shear. And when we design the bending moment, we design only for normally major moment is designed for this one, but what we do in the program will design this one as a column and design the bending moment in that axis as well. But mostly this moment is constant because that the axis is very that axis thickness is very small, so the moment will be minor moment. The main thing is shear. You have to design the in-plane shear. This is important. And we provide the horizontal reinforcement parallel to the shear force. We do not need to design the shear reinforcement in this direction. But in columns, you have to design for both directions. So, to get the design forces, you have to assign the pier level. And to provide the rebar information for the design, you have to go to design options, design menu, and shear wall design, and define pier sections for checking. Okay. That pier section is different from the one that you defined for forces. For example, okay, I will add the pier section. I will explain to you this. three types of pier section for the design. Here in shear wall design, there are three types of section. One is simplified C&T section, another one is uniform reinforcing pier section, and the third one is general reinforcing pier section. So for simplified C&T section, that one is compression and tension forces at the boundary of the planar wall and calculate the coupled moment. That simplified C&T can be used only for the planar wall. It is not suitable for this kind of C-shaped wall. But for uniform reinforcing pier section, you can use for any type of wall. This is the wall, and if you use simplified C&T section, the program will define the boundary zone at the edge of the wall and calculate the reinforcement and calculate this is for tension, this is for compression, and calculate the bending moment using that reinforcement. If that reinforcement is not enough, it will extend this boundary zone length to the middle and calculate the axial load capacity and bending moment capacity. But we never use this pier section because there is limitation that can be used only for the planar wall. Another one is uniform reinforcing section. If you use the uniform reinforcing section, then you have to define the uniform vertical reinforcement for that section. For example, for this wall, if you want to use the vertical reinforcement of diameter 20 at 200 millimeter spacing, you just define it. The program will provide the uniform reinforcement in the shear wall, in the pier section, and then calculate the capacity of the wall. Calculate the capacity curve of the wall and check with your demand forces. If the demand forces are inside the curve, the program will use that reinforcement directly. But if the demand forces are outside the curve, for this the 20 at 200 millimeter spacing, the program will increase the vertical reinforcement ratio gradually. For example, 1%, 2%, 3%, something like that. So it will make the iteration to cover this demand one. But the program will use the uniform reinforcement layout. The last one, general reinforcing pier section, can be used for this uniform reinforcing can be used for any shape of wall. Like if you use for C-shaped wall, if you use this 320 at 200, the program will provide uniform reinforcement along the length of the wall and calculate the PMM curve. The last one is general reinforcing pier section. When we design the shear wall, normally we do not provide the uniform reinforcement throughout the length of the wall. It is not economical. We provide the reinforcement, large reinforcement at the boundary zone, and this middle zone reinforcement is small reinforcement. That kind of reinforcement layout we have to use general PS section. If you use the general PS section, you have to draw the rebar layout in the program, and the program will use that rebar layout to generate the capacity curve and check the design. So if you use, for example, at the boundary zone, you use 2% rebar ratio, and middle zone 0.25% rebar ratio, and 2%. So the program will construct the capacity curve using this reinforcement. If it is not enough, it will increase, right, the reinforcement using this rebar ratio. So another one will be if it is 4%, 0.5%, 4%, something like that. It will increase the reinforcement and check the design. So I will show you uniform rebar section and general rebar section design in this model. I'll show you this wall in 3D. If you want to use the uniform rebar section, just select the wall, go to design, shear wall design, assign pier section, and uniform pier reinforcing section. Then the program will ask you which material are you going to use, which rebar size and spacing are you going to use. So I'll use concrete 8000 and rebar diameter 20mm dia and spacing of 200mm, and the cover is about 1 inch, and end corner bars, same bars, and then you have to select to be designed or to be checked, like the columns. If you select to be designed, the program will calculate the required reinforcement ratio and report you. If you use reinforcement to be checked, it will construct the PMM curve using this reinforcement and provide you the EC ratio of the shear wall length. So there is no iteration, just one time. But to be designed, you have the program will do the iteration for the design and provide the rebar ratio. First, I will use reinforcement to be designed. Here you can see I am providing diameter 20, 200mm spacing each face is to be designed. Go to design, and first I will select the design combos. I will add a few combinations of and go to design, shear wall design, and start design and shell structure. after you design, you can see the required reinforcement ratio of the wall. Here, go to design, display design information, and you can select longitudinal reinforcing, and you can also select the reinforcing ratio. If it is PR longitudinal reinforcing, it will show you in area. Second one is in rebar ratio, but you cannot see the DC ratio. I will show you rebar ratio. The program is providing 0.3% rebar ratio for this shear wall.
The crossing?
Yes, of the cross section. Is providing the minimum amount. Which one is the earthquake zone combination?
6, 7.
6, 7. That's why the forces are small and
After 5 we can add up to 7.
I will be deciding what is the one. Now it is increasing. Previously only 0.3%. Now it is 1.2%. You have to multiply with 100 to see the percentage. So in shear wall design, you have to design for the PMM capacity as well as the shear capacity. Program will, this one is for PMM, and for the shear, this is for shear reinforcing, but now the program is reporting in area per length. This one is inch square per feet. If you change the unit to millimeter square per meter, you will get the shear reinforcing using in SI unit. The shear reinforcement provided by the program is AV divided by S. So in your shear wall, you provide 2 legs. This one, the thickness is 500. So shear reinforcement is, let's say, 12 and 150. Okay. So you have 2 legs. So AV will be 2 into 12 millimeter diameter is 113 millimeter square cross sectional area. So the AV will be 226 millimeter square, and you have to divide by spacing. spacing is AB divided by, let's say 100 millimeter spacing. So it will be 226 millimeter square per 126 millimeter square per millimeter. Okay. So this is the required shear reinforcement. The program is so the program will give you this value. So after getting this value, you have to convert that area to the rebar diameter and spacing. If you want to use 12 millimeter dia, you have to calculate the spacing. If you get this value, if you use 12 millimeter dia, it will be 226 millimeter square divided by this value. You will get the spacing value. You have to check the boundary zone element, because in shear wall it has to resist the bending moment. There will be large stresses at the edge of the wall, compressive stresses at the edge of the wall. So to get the good ductility in concrete for compression, you have to provide the proper confinement at the edge of the wall to behave, to provide so the shear wall will behave with more ductility. Otherwise, if the compressive stress is very high, there will be crushing failure at the edge of the shear wall. So we have to check the boundary zone requirement based on the compressive stress of the concrete at the edge. If the compressive stress is very high for this certain length, you have to provide the proper confinement. This middle zone will not need the confinement. Here it is reporting the boundary zone requirement. This is the length of the boundary zone that you have to use. If you want to see more detailed results, you can right click on the shear wall and then you can see which is the control load combination for design. This is 6A is controlling. This is the design compressive force. This is the design moment. And this is for shear design. And this is for boundary zone element check. But the program will not give you the area of the confinement reinforcement in the boundary zone. The program will just give you this length. You have to calculate the confinement reinforcement area according to the code and provide the reinforcement. And I will continue for general reinforcing section. For general reinforcing section, you cannot define like uniform reinforcing section easily. In uniform, you just select the shell element and assign the diameter and the spacing. But for general reinforcing section, you have to draw the reinforcement. Go to design, shear wall design, and define pier sections for checking, and you have to add pier section. I will give design pier section for SW1 using 8000 psi. There are two options. One is you can draw the pier section start from scratch, Another one is use the geometry of the pier section that you define to extract the force, not for the design. Previously you defined the SW1 to extract the force. That one can be used to get the outline of the pier section. First, I will show you a new pier section without using force pier. Start section designer. It is starts from scratch, and then you have to draw the section, shear wall section using that one. But that one we do not use. I will start from existing wall pier. So you can select any story. Now shear wall is uniform throughout the building height, so I can use any story. And pier name is SW1. If you have the pier name, force pier name for other piers, there will be many piers here. Now I have only one pier, SW1, and click section designer. So the program will automatically generate the shear wall leg according to the model. If you want to modify but the program default is just providing the uniform reinforcing section. You can right click on the section and reinforcing yes, or if you want to draw again, you can make it no. It will delete the rebar, and you can draw the reinforcement. Okay, I will draw the reinforcement at the boundary zone. Here, go to rebar, draw menu, and click this one. This one will give you the, and you can adjust the. You just right click. Just right click the rebar and change the diameter and number of pass. For example, at the boundary zone, if you want to use larger diameter, you can change, and also smaller spacing. Okay, it will give you and if you want to adjust the size, you can adjust it. Click this one, and you cannot find how to adjust the length. I will draw the line. It is easier. Here you can draw the line. This is This is for boundary zone, and you can adjust the rebar here. Another boundary zone I will draw. And if you want to increase the bar size, you just right click on it and then change it to 6,000. And change the spacing and diameter. You can change line element. And for the middle zone, you can draw the smaller one. You can change the size here. Then after you adjust, just click done and click OK. So you already defined the pier section for design pier section for that shear wall. Then you have to select the pier shear shell elements again and design shear wall design. Assign pier section for checking and general rebar pier section. Then you have to select this PSW1 and select reinforcement to be designed or to be checked. So it is already defined, it is already assigned. Then you select it and check again. So after you design, you can see the same information. Don't know what happened to the graphic, it is not sure. But when I right click, you can see.
What's the graph?
I mean, I cannot see the rebar ratio here. But anyway, you can right click and see the rebar ratio. Okay, this is the required rebar ratio, 1.2%. And this is for shear design. This is for zone element. So this is the shear wall design procedure in ETABS, and also you can extract these results from two table. Okay, shear wall design, and so you will get the table format. Required rebar ratio, current ratio. I will show you another thing. Now I design for planar wall only, but if you design for the C-shaped wall, you have to select the C-shaped, entire C-shaped wall. this C-shaped wall. Show you. If it is C-shaped wall, for the PMM design, you have to select all the legs and design. But for the shear design, you have to design leg by leg. You cannot combine all three legs, leg by leg and design. So I will define the pier section for this one. For force, assign shell pier label and say SW2.
For each section you have to define the pier.
Yes, the entire one I will assign as a pier label. Then I will show you the general rebar section. Design, shear wall design, and define pier section. Previously TSW1 I designed for this planar wall. Now this one I will define for C-shape. I will start from existing pier, 3000 psi. Then I will select any story. This time you can see SW2. SW2 section designer. Then the program automatically draw, and then you redraw the rebar. There's some I define as pier PSC1 and then assign this one back. Design, shear wall design. Assign pier section for checking, general rebar. Then you have to select this and reinforcement to be designed. So it will assign to this pier and then you can design. Then design, shear wall design, start design and check structure. So the program will design the PMM using the C-shape section. But shear wall, shear check, the program will design leg by leg and provide you the reinforcement ratio for shear leg by leg. I will explain you the code provision for the shear wall design using ACI code. Shear wall design is taking time because it has to construct the PMM curve for each wall and check the design. So in shear wall, you can see this is for boundary zone, this is for middle zone, where this one is providing the confinement reinforcement. So there are three types of reinforcement. One is the vertical reinforcement, another one is the horizontal reinforcement, and the third one is the boundary zone confinement reinforcement. So vertical reinforcement will resist the PMM flexure domain. Shear horizontal will resist the shear domain. And in the code, the minimum reinforcement ratio for the shear walls in the tall building is 0.25%. The ratio is. So you cannot provide less than that ratio. Both vertical and horizontal rebar is 0.25%. But if the shear stress is very small, you can reduce the, you can use less than 0.25. And another thing is, if your shear wall is very short, the squat wall, HW over height of the wall and length of the wall ratio is less than 2, the transverse reinforcement should not be less than the vertical reinforcement, because the shear will be dominating in that design. For the sizing, minimum thickness requirement, there is no limit in ACI 318. But you better to provide minimum thickness of 8 inch as a lower limit for the structure wall, which is about 200 millimeter. But it is still small for the construction, so you should use at least 300 millimeter 12 inch where the horizontal elements are used. But if the walls are coupled walls connecting by the coupling beam, you should provide larger than that. With the walls with the conventional reinforced coupling beam, you should use at least 14 inch, and with the diagonal reinforced coupling beam, you should use at least 16 inch for the constructability issue. For example, in elevation, you have the wall, and we couple the wall with the beams. So conventional reinforcement is just provide the longitudinal reinforcement in the beam. But for the diagonal reinforced, you are providing the diagonal reinforcement like this. So to accommodate this reinforcement inside the wall, you should use at least 16 inch. Otherwise, at the corner, the rebar will be very congested. There are 3 types of walls: slender walls, where H over LW is more than 2, which is behaving as a cantilever mode. Flexure is dominant, and we allow inelastic behavior for flexure yielding. And for the squat wall, which is short wall less than 0.5, and another one is aspect ratio between these two. For the squat wall, shear will be dominant. This is the slender wall, where the yielding can be occurred at the base of the wall. For the seismic loading, we allow yielding, but we have to design to remain elastic for wind loading. But for the tall building, not only at the base, we allow the yielding maybe at the mid height of the shear wall because of the diamonds effects. Here, these are the couple walls. The yielding will be occurred not only at the base of the wall, but also at the coupling beams. But we do not allow the yielding in shear in the shear walls, because that one is brittle behavior. This one is explaining about the detailing requirements. Special detail for the tensile response can be concentrated around the selected critical sections. That one is the confinement requirement. If you want to allow the yielding at the base of the wall, you have to provide good confinement at the base. If the yielding also allowed in the mid height of the wall, you should provide the confinement at the mid height as well. This is for tall building, the yielding can occur in the intermediate stories. in UBC 97, there is a limit of the axial force in the shear wall. That axial force should be less than 0.35 P naught. That P naught is the axial capacity of the wall. This is the PMM diagram of the wall. This is axial force, moment. This is the axial force capacity, and this in the shear wall, the axial load should be lower than this one. It means that the load intention is the axial compressive force should be lower than balance point, because in PMM curve, above the balance point it will become brittle, below the balance point it will become ductile. So the code is limiting that one 5.35 P naught. This 0.35 P naught is approximately this point, but this is true for only planar walls. But for the complicated shapes, this one might not be always true. So if the axial force is more than this one, the code doesn't allow to use that shear wall as a lateral load resistance system. But in ACI 318, there is no limit about the axial force. But the concrete strain should not reach the concrete compressive strain should not reach 0.003 before the rebar strain reach the 0.002. It is like in the beams, when you over reinforce the beam will fail in brittle moment. To avoid that behavior, the ACI 3186, the concrete strain should not reach, concrete should not yield before the steel yield. These are the preliminary proportioning of the shear wall. It is for planar. This one is good for planar wall. It looks like a simplified TNC section procedure in ETABS. This is for boundary elements. Special boundary elements are required for the high compressive command at the edge, and ordinary boundary. If the compressive stress is not high, you can use the ordinary boundary element. But in the code, it specifies only for the special boundary element. Ordinary boundary element is just providing the normal ties on the particle to confine the particle mass. To specify to determine the special boundaries of element, there are two methods. One method is calculating based on the lateral displacement at the top of the wall and calculate the neutral axis depth of the section, and based on that it calculates the boundary zone length. So that method is complicated because to calculate this you have to calculate the displacement. You have to analyze first and calculate this lateral displacement for lateral load equate H case and divided by HW and calculate and check C. Check with the neutral axis, and if it is less than that, you have to provide the confinement boundary zone element. This is the sample of boundary zone element that is provided. For the lower level, there will be because there will be large moment and large compressive stress, so we have to provide good confinement. At the upper level, if the stress demand is low, you can provide the boundary zone, ordinary boundary zone element. And the upper level, if not required, but we should provide at the boundary zone for some tiles to tie the vertical elements. Can be used for the planar wall, but for the complicated C shape and other shapes, the method 1 is not appropriate. So another method is it can be used for any shape of wall. We just check the stress, concrete stress in the concrete. Just check the stress is exceeding 0.2 Fc prime or not, and then you can you extend the boundary zone length based on where the stress is lower than 0.15 Fc prime. For example, this wall, I will you have to check S22. What is that one? Case.
Vertical stresses.
Yes, vertical stress, because compressive stress will be vertical. So you can see the stress contour. Okay, what is this? Stress fiber. Okay, this is about 10 megapascal. So in the code, it says that if the concrete stress exceeds 0.2 Fc prime. So, for example, if your concrete stress is concrete Fc prime is 41 megapascal. So 10% will be 20% will be 8 megapascal. So if now your concrete compressive stress from the analysis is 10 megapascal, so you need that boundary zone element and check the stress contour in analysis, and where you can get the, if the stress is lower than 0.15 Fc prime, you can stop the boundary zone element. Okay, this is the sample boundary zone element. And this reinforcement, this reinforcement area has to be calculated using this equation. Okay. In this one, S is the particle spacing, and H is the, if you have 3 legs, you have to sum the cross-sectional area of 3 legs, and then you can calculate the spacing. And alternate vertical bars has to be confined in the special boundary zone element. You cannot skip. Okay, for example, you provide the confinement here, and then you provide only here, and if you skip 2 bars, you cannot do that one. You have to skip. You can skip only 1 bar. This is for ordinary boundary element. If stress is very low, you can provide that ordinary boundary zone element. This is ordinary boundary element. Ordinary boundary element doesn't have the equation to be calculated. Just follow ACI 318 section 7.10.1. This is the shear wall design procedure. First, you have to determine the what is the boundary zone length and what type of boundary zone element required. Then you calculate the number of legs of the confinement reinforcement in the boundary zone. Then you have to provide the vertical reinforcement according to that confinement bar layout and calculate the PM curve. Then you have to check the design using that PM curve if it is enough or not. Another one is first select the vertical reinforcement and spread the spread in the boundary zone element and calculate the layout of the transverse confinement reinforcement. This is for shear design. For shear design, there are three equations to check the shear capacity of the wall. In shear wall, you cannot consider the axial force, compressive force in the shear capacity calculation. In column, in column shear design, you can consider the axial compressive force. If you have the larger compressive force, your shear capacity is increased. But in shear wall design, you cannot consider, just use concrete and steel. And then you have to check the upper limit of the shear wall shear stresses. For example, if the shear stress shear demand is, for example, 10,000 kilonewton. Your shear capacity calculated from this equation is 8,000 kilonewton only. So if this equation doesn't consider the horizontal reinforcement, shear reinforcement. The above equation consider the horizontal reinforcement. So if you provide too much horizontal reinforcement, you can increase the capacity more than the demand. But the code doesn't allow. If this is the maximum limit. If the shear capacity calculated from this point is 8,000, you have to use that value. Although you got the shear capacity from this equation is 12,000 or 13,000, this one will be 11. And for this one, if you have the in your building, in the plan, you have one shear wall and another shear wall, like this to resist this shear force. So 1, 2, 3, 4 legs are resisting common shear force. So this average shear stress also needs to be checked. You have to calculate the shear capacity using this equation, or using this 1, 2, 3, 4 legs, and calculate the demand, get the demand in those legs and compare it. If that demand is lower than this value, it is okay. If not, we have to increase the thickness of the wall. So that's all for shear wall design.